Hello and welcome to a brief history of the study of the universe. Lecture 1 in my 6-part lecture series, Cosmology, the Study of the Universe. My name is Fulvia Fiorani. In this lecture, we take a look at the study of the universe from a historical perspective. We will start with what we know about the universe today, and then we'll go back in time and follow a chronological path of observations, discoveries, theoretical work, and technological advances that will take us from the ideas of the ancient Greek astronomers and philosophers to our current understanding of the universe today. This lecture also serves as a historical backdrop upon which the other 5 lectures will unfold. So we start with what we know about the universe today. Our observable universe is 13.8 billion years old. When we say that the age of the universe is 13.8 billion years old, what we mean is that the universe has been expanding for 13.8 billion years. The universe started to expand at a moment which we call the Big Bang. We do not know what happened at the actual moment of the Big Bang, and we certainly do not know what happened before it, but we have a pretty good idea of what happens just fractions of a second after. So at the beginning of time, all of space, time, matter, and energy was contained in a region of infinite density and 0 volume. And for reasons that are really not known, the universe expanded from this initial extremely hot and dense state and evolved into the very cold and sparsely populated universe of stars and galaxies we see today. The expansion rate of the universe slowed down for the first 9 billion years, as we would expect due to gravity. But surprisingly, during the last 4.5 billion years, the expansion has been accelerating. We call whatever it is that's causing this acceleration dark energy. Our best observations today indicate that the universe is made of 5% ordinary matter, all the planets, stars, and galaxies that we see out there, about 25% dark matter, although unseen and yet to be discovered, there is abundant gravitational evidence that it exists, and about 70% dark energy, propelling the accelerated expansion of the universe. Now, these numbers are approximate, but they're easy to remember, and we'll see more accurate figures in the last lecture. Okay, so now that we've covered what we know about the universe today, let's see how we got there. We will start our history with the ancient Greeks and their ideas of a geocentric or an Earth-centered universe. Then we move forward about 1,500 years to the idea of a heliocentric or a sun-centered universe as proposed by Copernicus, observationally proven by Galileo, and theoretically explained by Newton and his law of universal gravitation. In 1610, Galileo records his first telescopic observations of the sky, changing forever how we view our universe. The birth of modern cosmology can be attributed to Einstein's general theory of relativity. We will see that the fundamental observation of modern cosmology is the discovery that the universe is expanding. The Big Bang theory is the current cosmological theory that describes the expansion and evolution of the universe. Although neither dark matter nor dark energy have been detected, our observations indicate that they must be out there. We will see how the recently discovered gravitational waves is a new tool to study the universe and ushers in a new era of multi-messenger astronomy. Of course, along the way, we will also cover the various technological advancements that allow us to better observe and study the universe. Before we start with the ancient Greeks, I'd like to say a few words about prehistoric and ancient astronomy. It is impossible to know when humans first looked up into the skies and wondered about what they saw. But some of the oldest cave paintings suggest that ancient people may have had a knowledge, or at least an awareness, of relatively advanced astronomy. Analysis of some of these cave paintings suggests that they are not simply depictions of wild animals as previously thought, but the animal symbols may be representations of star constellations used to mark astronomical events such as comet strikes. Ancient civilizations such as Babylonians, Egyptians, Chinese, Maya, and Hindus made celestial observations for a practical nature. They observed the motions of the sun, moon, and planets to create calendars to remind them of important annual events, such as when to plant and harvest crops. They also made observations of the positions of stars to assist in navigation. And some of these observations were of an astrological nature, or the study of how the relative positions of various celestial bodies would influence human affairs. Some cultures left behind extensive documents, while others left behind structures with significant astronomical alignments. Although these ancient civilizations made great astronomical observations, their cosmologies were mainly mythological in nature. Our modern physical cosmology has its roots in the ideas of the ancient Greek philosophers and astronomers. The ancient Greeks were the first to take a theoretical and scientific approach to explain the behavior of celestial bodies. In other words, they tried to explain observations by understanding the underlying nature of the universe. We start with Aristotle, the most famous of ancient Greek philosophers. He introduced observation as an important step in understanding the world, and believed that thought alone was sufficient to explain the natural world and the rules that govern the motion of bodies, both terrestrial bodies and celestial. He didn't have much regard for experimentation and considered it somewhat below the level of pure logical thought. Sort of like Sheldon, the theoretical physicist, looks down upon Leonard, the experimental physicist. But back to Aristotle. Aristotle divided the universe into terrestrial spheres, which were corruptible and where humans lived, and celestial spheres, which, although they were moving, they were unchangeable and were the realm of all celestial bodies. He believed that the universe was made of 5 elements. The 4 classic elements of earth, water, air, and fire made up everything in the terrestrial sphere, and then these elements would combine to form all other terrestrial elements. The celestial bodies were made of a weightless and incorruptible or an unchangeable 5th substance called the ether. The motion of terrestrial elements was always toward their natural place. The natural place for Earth is in the center of the universe. So, for example, if you drop a heavy object, it will move toward the center of the universe. The natural place for fire is in a sphere above water, so it will rise to its natural place. The motion of celestial bodies, which are embedded in perfectly concentric spheres, rotate eternally and at a constant rate. So Aristotle's universe is perfect, eternal, finite, and very importantly, Earth-centered. Of course, a centered and stationary Earth made a lot of sense at the time. After all, as seen from Earth, the stars, the sun, the moon, and the planets all seemed to rise in the east and set in the west. So it was natural to think that everything moved around the Earth. The planets were also observed to slowly move from west to east among the backdrop of the fixed stars from night to night. And sometimes the planets were mysteriously seen to stop in their forward motion, reverse their direction of travel for a while, then resume their forward motion. So there's a lot of motion of celestial bodies as seen from Earth. So Aristotle developed a system to make sense of all this motion. According to Aristotle, the universe is made of concentric spheres, with the stationary Earth at the center and the firmament of fixed stars in the outer sphere. The sun, moon, and planets were each embedded in their own spheres. And to make sense of and to account for all the various motions, the Aristotelian system had 55 nested spheres, all influencing each other's motions. So needless to say, this was a very complex system and had very limited predictive powers. In other words, it was not able to predict the position of celestial bodies as a function of time. Before we get to the person who did come up with a good system to predict the motion of heavenly bodies, I'd like to mention two lesser-known but very important Greek astronomers. The first is Aristarchus of Samos. By measuring the angle between the moon, the sun, and the earth during the phases of the moon, he was able to calculate the distance to the sun and the moon. Now, although his calculations were off, his approach was correct. And through his measurements, he correctly deduced that the sun is very large and distant. And he reasoned that since the sun is considerably larger than Earth, it was probably the dominant object in the universe. But more important than his astronomical contributions, Aristarchus was the first to put forth a heliocentric hypothesis that the Earth and the planets orbited the sun. Unfortunately, his radical theory was not accepted at the time and was rejected in favor of the more common sense Aristotelian system. 1700 years later, Copernicus would attribute his heliocentric theory to Aristarchus. Next, we have Hipparchus. He is perhaps the greatest astronomer in antiquity. He refined Aristarchus' distance to the moon to within 2% error from the actual value. He determined the length of the year to within 6 minutes. And he compiled the first accurate catalog of 850 stars, including their positions and their relative brightness. This was the first attempt at a classification of stars. His measurements of the North Star Polaris were so accurate that he noticed the direction of the North Celestial Pole gradually changes in time. And he is credited with the invention and improvement of several astronomical instruments which were used for a very long time for naked eye observations. And so we finally come to the last of our great ancient Greeks, Ptolemy and his geocentric model of the universe. Ptolemy elaborated on Aristotle's idea of the Earth-centered universe into a complete cosmological model. Ptolemy's system, although still Earth-centered, was much less complex than Aristotle's 55 nested spheres. And more importantly, it had much better predictive powers. In other words, it could correctly predict the position of bodies as a function of time. Now, this is a diagram of the Ptolemaic system with the stationary Earth at the center, surrounded by 8 concentric spheres that carry the moon, the sun, the 5 known planets, and the fixed stars. The fixed stars always stay in the same position relative to each other, but rotate across the sky. We also notice that each of the planets move along a smaller circles as they go around the Earth. These are called epicycles, and Ptolemy introduced them to explain the retrograde motion of planets. Various other adjustments also had to be made to fit his model to the observations. Now, although the Ptolemaic system is still a fairly complex model of the universe, it was a reasonably accurate system for predicting the positions of heavenly bodies in the sky, so much so that it was used for the next 1,500 years until Copernicus came along. In 1514, Nicholas Copernicus revolutionized the study of the universe by proposing a heliocentric model. Recall that almost 2,000 years earlier, Aristarchus had first suggested a heliocentric system, but that was not the system that came down to us from the ancient world. Heliocentric, of course, means sun-centered. Here we see a copy of his notes taken from his most famous work on the revolution of heavenly bodies, where the sun is stationary while the Earth and the 5 known planets moved in circular orbits around the sun. The Copernican model got rid of Ptolemy's celestial spheres and with them the idea that the universe had a natural boundary. It was much simpler, beautiful, and elegant theory than Ptolemy's. However, the theory's power to predict the positions of heavenly bodies was not any better than Ptolemy's. There was no real evidence that the Earth was moving. After all, from the point of view of an observer on Earth, we certainly do not seem to be moving. And then it contradicted the Bible, which at the time was considered not only to contain theological truth, but scientific truth as well. Of course, most of us today do not consider the Bible to be a science book. In fact, one of my favorite sayings is, "The Bible teaches us how to go to heaven, not how the heavens go." Needless to say, Copernicus's theory was not accepted by many during his time, and it would take almost 100 years before his theory was taken seriously. And finally, in 1610, Galileo would observationally prove the Copernican system to be correct. Before we talk about Galileo, I'd like to mention two astronomers who contributed greatly to calculating the positions of planets and refining the Copernican system. We start with the Danish astronomer Tycho Brahe, who took observational astronomy to a whole new level of accuracy. Brahe was also a very successful astrologer, and soon he discovered that there were problems with his astrological predictions. Brahe discovered that neither of the two sets of astronomical tables, the Ptolemaic nor the Copernican, gave him accurate positions of the planets. So he decided to dedicate his life to calculating the positions of planets as accurately as he could. And so, over a 20-year period, he compiled all his data into the greatest catalog of observations by the naked eye. But Brahe wanted to do more than simply accurately record the positions of planets. He wanted to predict what would happen to the planetary positions in the future. Unfortunately, he did not have the mathematical skills to make the most of his data. In 1610, Brahe met Kepler, a German astronomer and mathematician. Whereas Brahe had all the data, but not the mathematical skills to formulate a theory to fit his data, Kepler had the mathematical ability, but not the data. So it was a perfect match. Using Brahe's highly precise observational data, Kepler formulated his famous 3 laws of planetary motion. Kepler's laws describe the motions of planets around the sun and refine and improve the Copernican system. Kepler's laws tell us that the path of planets around the sun are elliptical, not circular, and their speeds vary depending on their distance from their sun. These laws can be used to correctly predict the position of planets at any time in the future. These laws can also be generalized for any orbiting system, natural and artificial satellites, stars around the centers of galaxies, and they can also be used to calculate the orbits of comets and asteroids to see if they are on a collision course with Earth. And so we come to Galileo. He is considered the father of modern astronomy, not because he was the first to look up into the sky and try to figure things out, we've certainly seen many before him, but because he was the first to use a telescope to study the heavens. He did not invent the telescope. That credit goes to the German-Dutch lens maker Hans Lippershey, but Galileo greatly improved on the device. In 1610, he published the first ever telescopic astronomical observations in a publication known in English as the Starry Messenger. The use of the telescope is truly the next great step on the road to a deeper understanding of the universe and would forever change the way we view the world around us. We mentioned earlier that Galileo provided the observational proof of the Copernican heliocentric model. So let's take a look at those 2 discoveries. The first was the moons of Jupiter. In January of 1610, Galileo observed what he described as 3 fixed stars all close to Jupiter and lying in a straight line through it. Observations on subsequent nights showed that the positions of these fixed stars were changing relative to Jupiter, therefore could not have been fixed stars. During one observation, one of the stars has disappeared behind Jupiter. Then later he observed a fourth star. Within a few days he concluded that these bodies were orbiting Jupiter. These are the sketches published in the Starry Messenger showing the different positions of the stars relative to Jupiter. Now these observations went against Aristotelian cosmology that all heavenly bodies should circle the Earth. This was the first time that heavenly bodies were seen to circle each other. This is Jupiter as seen through a small telescope. Even today, this is a beautiful sight to see. Today, these 4 moons are called the Galilean satellites. The second set of observations supporting the sun-centered model were the phases of Venus. Starting in September of 1610, Galileo observed that Venus exhibited a full set of phases similar to those of the moon, as seen in these sketches. This proved conclusively that Venus must orbit the sun. And this is a composite image of Venus taken in 2004. And the phases of Venus can easily be seen with a small backyard telescope. When Galileo turned his telescope to the stars, he got another surprise. The stars still appeared as tiny, unresolved points of light, reinforcing the notion that they were very far away. And when he pointed the telescope at the space between the stars, more and more stars appeared. He discovered that there were many more stars out there than anyone had ever imagined. The next figure on our road to modern cosmology is Sir Isaac Newton. He is one of the greatest and most influential scientists of all time. He was an English mathematician, physicist, astronomer, and theologian. He is considered the father of physics. His laws of motion give us a very comprehensive theory that is still in use today. They describe the relationship between a body and the forces acting upon it, and the body's motion in response to those forces. We will not talk about these laws today, but they are the foundation for classical mechanics and classical physics. We could spend a whole course on Newton alone, but we will focus on his main contributions to cosmology. The first contributions are in the field of light and optics. Newton discovered that prisms could separate white light into different colors. He called this the spectrum of light. We will see that we can learn quite a lot by analyzing spectra of objects in space. Another main contribution from his studies in optics is the invention of the reflecting telescope. Almost all major telescopes used today in research, including the Hubble Space Telescope, are reflector telescopes. But Newton's most important contribution to cosmology is his law of universal gravitation. With this law, he provided the insight into planetary motion that enabled cosmology to become a modern science. It is often said that Newton's theory of gravitation was inspired by the fall of an apple. He reasoned that if the apple always falls straight down toward the center of the Earth, then the Earth must draw it there. If matter draws matter, it must then be in proportion to its quantity. Therefore, the apple draws the Earth as well as the Earth draws the apple. Newton contemplated this drawing force, what we call gravity today, and was convinced that every object in the universe had a gravitational attraction to every other object. In essence, he showed how the whole system of the sun and planets could be explained from a single law, the law of universal gravitation. Here it is in its mathematical form. This simply states that the force of gravity, F, is proportional to the product of the masses of the bodies, so the larger the masses, the stronger the gravitational force, and it's inversely proportional to the square of their distance. So if you double the distance of the two bodies, the force of gravity goes down by a factor of 4, and if you triple their distance, the force of gravity goes down by a factor of 9. G is the gravitational constant. It's a very small number, as you can see here. So gravity actually is a very weak force. Newton's great insight is that the force of gravity works not just on Earth, but throughout the whole universe. So gravity is universal. In other words, every particle of matter in the universe exerts a gravitational attraction on every other particle in the universe. This is a very key concept as we study the evolution of the universe. By the time of Newton's death, his laws of motion and universal gravitation, coupled with Kepler's laws of planetary motion and Galileo's use of the telescope, provided future scientists with the tools they needed for the development of modern cosmology. Armed with these tools, astronomers set out to explore the cosmos by looking deeper and deeper into space. Sir William Herschel, a German-born British astronomer, was the most influential astronomer of his lifetime. He was greatly supported in his observations and discoveries by his sister Caroline, who herself is credited with the discovery of 8 comets. He is most famous for the discovery of the planet Uranus in 1781. It was the first planet discovered in the modern era. The other 5 planets had all been known since antiquity. This discovery launched his career, and he was appointed as the court astronomer by King George III. With this appointment, Herschel could afford to build bigger and better telescopes to study the skies. He greatly improved the reflecting telescope by casting and grinding his own mirrors. And by the time he had mastered all the optical techniques, he was building the best telescopes in the world and was able to see much farther into the sky than ever before him. With his greatly improved telescopes, he initially focused his work on a systematic observation of the stars, specifically double and multiple star systems. He then set out to conduct a survey to observe the fuzzy objects known as nebulae. His observations through 20 years of systematic sweeps of the deep sky resulted in the publication of 2 catalogs listing 2,500 nebula and star clusters and over 800 double or multiple star systems. Herschel also studied the structure of the Milky Way and was the first to propose a model of the galaxy based on observation and measurement. Through his observations, he made 2 major discoveries that had an important bearing on our understanding of the cosmos. First is that we live in a huge collection of stars known as the Milky Way, which at the time was considered the entire universe. He observed that the distribution of stars is not evenly distributed in all directions, but the stars seem to clump together and lie in a disk-like configuration, as we see here in the first map of the structure of the Milky Way galaxy. The second discovery was related to nebulae. During the course of his deep sky surveys, he began to speculate on the nature of these nebulae. He found that some of the nebulae consisted of stars and postulated the existence of island universes, what we call galaxies today. Lastly, he observed that some of the star clusters were more dense than others. So he argued that these clusters must coalesce under the force of gravity, and that the groups of more widely scattered stars must be at an earlier stage of development than the more tightly packed stars. In essence, he became the first to describe the universe in evolutionary terms. In the second half of the 19th century, a new way of viewing the stars emerged using a technique called spectroscopy. Recall that Newton discovered that shining white light through a prism would separate it into individual colors or wavelengths, and form what is known as the visible spectrum. It was discovered that as light passes through a gas, some wavelengths are absorbed, leaving a pattern of spectral lines called absorption lines. Around 1860, it was discovered that each gas or element creates its own unique spectral pattern. In essence, each element has its own fingerprint. It was then quickly realized that by analyzing the light from a star, it would be possible to determine its chemical composition. Sir William Huggins and his wife Margaret were among the first to apply spectrum analysis to astronomy. In 1863, they showed that stars are composed of the same elements that occur on the Sun and Earth, demonstrating that stars are indeed suns and the Sun is a star. In 1868, they made an important discovery that would have profound importance in the study of the structure and evolution of the universe. When observing the star Sirius, they noticed that the spectral lines were shifted toward the red end of the spectrum. In other words, they were redshifted, concluding that Sirius is moving away from us. This discovery would eventually lead to the discovery of the expanding universe. The next giant step in observing the universe was photography. Until then, astronomers had to record their observations by hand. Not only could astronomers now keep an objective record of their observations, but this new technology would allow them to detect previously invisible objects. The use of astrophotography has revolutionized our understanding of space. Henry Draper, an American physician and amateur astronomer, was a pioneer of astrophotography. In 1872, he succeeded in taking the first photograph of a stellar spectrum, showing distinct spectral lines when he photographed the star Vega. He took over 100 photographs of stellar spectra before his untimely death in 1882. In an effort to carry on her husband's work, his widow, Anna Palmer Draper, funded an endowment to finance the compilation of the Henry Draper Catalog of stellar spectra. In all, about 360,000 stars were classified. Henry Pickering, the director of the Harvard College Observatory, picked up the baton to produce the detailed star catalog. Pickering's challenge was to establish a system of analyzing all the photographic plates. Each plate contained hundreds of stars, which all had to be evaluated by brightness and location. Pickering initially recruited a team of young men to carry out this task, but soon he became frustrated with his team's lack of concentration and attention to detail. Legend has it that in frustration he declared that his maid could do a better job. Well, his maid was Williamina Fleming, and Pickering did in fact hire her to start cataloging the stars. Pickering eventually fired his male assistants and hired all female computers, as we see here with Williamina Fleming in charge. Fleming devised a system of star classification according to the amount of hydrogen in their spectra. During her time at the observatory, Williamina cataloged over 10,000 stars and discovered 59 nebulae, including the famous Horsehead Nebula. Another one of the computers was Annie Jump Cannon. Cannon had a degree in physics when she came to work for Pickering, and she improved on Fleming's system by introducing a star classification based on temperature. Her new method classified stars as O, B, A, F, G, K, M. The usual mnemonic is, "Oh, be a fine girl, kiss me." This classification is still in use today. Of all the female computers, Henrietta Leavitt had the greatest impact on cosmology. We will talk more about her significant contributions in a few slides, but for now I'll just mention that she made a discovery that would eventually lead to measuring the universe. And so we come to Einstein. His theories of relativity can be considered the birth of modern cosmology. In 1905, an heretofore unknown patent clerk in a Swiss patent office published one of the most famous papers in the history of physics, which would eventually be known as the special theory of relativity. Until this time, space and time were considered absolute. In other words, they were the same for everyone, and they were considered fixed, or they did not change. Space and time existed separately from one another. This was the intuitive world of Newton's classical physics. But Einstein changed all of that. According to special relativity, space and time cannot be defined separately from each other. Instead, space and time are two aspects of a single continuum known as the four-dimensional space-time. Another consequence of special relativity is the mass-energy equivalence, better known in its equation format, E equals mc squared, quite possibly the most famous equation in physics, if not of all sciences. This equation states that energy is equal to mass times the speed of light squared. Now, since the speed of light squared is such a huge number, then even a small amount of mass equals a very large amount of energy. Basically, what this equation tells us is that energy and mass are interchangeable. They are essentially the same thing. Now, for cosmology, a crucial point about either mass or energy is that they both generate gravity. Which brings us to Einstein's general theory of relativity, which is the current description of gravitation in modern physics. Perhaps Einstein's greatest insight is that the very structure of space and time, or space-time, is dynamical. In other words, space-time can actually change. The very fabric of space is flexible. So space-time curves in the presence of mass and energy. The amount of curvature is determined by the amount of mass and/or energy. Here is a two-dimensional representation where the grid lines represent space and how they are warped by the presence of a massive object. Gravity, thus, is simply a manifestation of the curvature of space-time. The classic example is a bowling ball on a rubber sheet. The bowling ball will cause the rubber sheet to curve or warp, as we see in this diagram. If we then place a marble near that curvature, the marble will move according to the curvature of the rubber sheet. If the marble has no motion, it will fall onto the bowling ball. If it has sufficient motion, it will dip toward the bowling ball following the curvature of the sheet, then eventually continue its forward motion. And if the speed is just right, it will circle or orbit the bowling ball. As the physicist John Wheeler cleverly stated, space-time tells matter how to move, and matter tells space-time how to curve. This is the equation of general relativity. It is known as Einstein's equation. This equation actually comprises 10 differential equations. And these equations relate the distribution of matter and energy with the geometry of space and time. As we will see, these equations completely changed how we understand the nature and evolution of the universe. So the theory of general relativity was beginning to suggest some disturbing ramifications about the universe. Einstein firmly believed in a static universe, as everyone else did at the time. But he soon realized that his equations suggested that the universe would be unstable and would collapse in on itself under the weight of its own gravitational mass. To stabilize a collapsing universe, Einstein introduced a cosmological constant to his equations. The cosmological constant, which he called lambda, was a feature of space itself and would counterbalance the effects of gravity to achieve a static universe. In 1922, the Russian mathematician Alexander Friedman solved Einstein's equations for a special case when lambda equals 0. He found a solution to the equations that describe an expanding universe. However, Friedman was a pure mathematician and considered his work interesting as a mathematical problem. It does not appear that he was interested in any physical applications. He also died very young and was not able to support his theories. Independently from Friedman, in 1927, Father George Lemaitre, a Belgian Catholic priest and theoretical physicist, also solved Einstein's equations and found solutions that supported an expanding universe. But unlike Friedman, Lemaitre applied the equations to cosmological questions and considerations, and would eventually develop a dynamic model of the universe. We will talk more about Lemaitre in a few slides. It must be said that initially Einstein criticized both Friedman and Lemaitre because he firmly believed in a static universe. Eventually, he would concede and apologize. So far, we've talked about the expansion of the universe in theory only. What was still missing, however, was observational proof. But before we get to that historic discovery, we need to mention the three main discoveries that led to the famous observation. The first was by Henrietta Leavitt, who you will recall was one of the computers at the Harvard College Observatory. Her discovery is one of the greatest breakthroughs of 20th century astronomy. Her job was to study the brightness of variable stars as recorded on photographic plates. She took a particular interest in a type called Cepheid variable stars. These are stars whose brightness varies with a regular period. What she discovered is that there is a relation between the luminosity of a Cepheid variable star and the period of its variations in apparent brightness. This discovery provided astronomers the first reliable yardstick to measure faraway objects in the universe. Unfortunately, Leavitt died in 1921, so she did not live to see the ultimate fruits of her momentous discovery. Harlow Shapley succeeded Henry Pickering as the director of the Harvard College Observatory. Using Leavitt's period luminosity relation, he was able to make the first reliable measurement of the size of the Milky Way galaxy. Instead of a relatively small system with the sun near the center, as had previously been thought, he determined that the galaxy is immense, about 100,000 light years across, and that the sun is nearer to the edge than the center. Although he was correct about the size of the Milky Way and the position of the sun, he was ultimately wrong in his belief that the Milky Way was the entire universe. Vesto Slipher made the first measurements of the velocities of spiral nebula, or galaxies as they are known today. He measured their velocities by measuring the Doppler shift of their spectral lines. Very briefly, the Doppler effect is the increase or decrease of a wave as an object moves away or toward us. The classic example for a sound wave is a siren. As the siren moves toward us, the pitch increases, and as it moves away, the pitch decreases. In the case of light, if an object is moving away from us, the frequency decreases and the spectral lines are shifted toward the red end of the spectrum. What Slipher discovered is that most spiral nebula are moving away from us. So now all we need is someone to come along and put all these pieces together. That someone was the American astronomer Edwin Hubble, considered the greatest astronomer of the 20th century. His first great discovery was made in 1924, when he found a Cepheid variable star in what was then known as the Andromeda Nebula. Using Leavitt's period luminosity relation, he was able to calculate the distance to Andromeda. He calculated a distance of 900,000 light-years from Earth. Recall that Shapley had measured the size of the Milky Way galaxy, what he considered to be the entire universe, to be 100,000 light-years across. Hubble's calculations clearly put Andromeda outside our Milky Way galaxy. The Andromeda Nebula became the Andromeda Galaxy. In other words, we are not the only galaxy in the universe. Later, it would become clear that many nebulae were also galaxies. And today, we know there are over 100 billion galaxies in our observable universe. In 1929, Hubble would once again change our view of the universe when he made what is considered the fundamental observation in modern cosmology. Recall that Vesto Slipher had discovered that most nebulae were moving away from us. But the reason for the motion remained a mystery. So Hubble and his assistant, Milton Humason, set out to try to solve the mystery. Humason measured the Doppler shifts of many galaxies, confirming Slipher's results, while Hubble measured their distances using Leavitt's law. With new data in hand, Hubble plotted velocity versus distance of each galaxy, and an astounding result emerged. The farther away the galaxy, the faster it was moving away. There was a clear proportionality between distance and velocity. What Hubble discovered is that the universe is expanding. This was the first observational evidence that would pave the way for the concept of the Big Bang. Now, when we say that the universe is expanding, what we really mean is that space itself is expanding. Not that galaxies are moving away from each other in some pre-existing space, but that space itself between the galaxies is expanding. Let's take a look at some of the cosmological implications of an expanding universe. First, we take a look at Hubble's data and the law derived from the data. Here is the first set of data from 1929. On the vertical axis, we have the recession velocity as measured by Humason, and on the horizontal axis, their distance as measured by Hubble. While the points do not all fall on the line, there is a general trend suggesting the speed of a galaxy is proportional to its distance. In 1931, after long nights at the telescopes and pushing technology to its limit, they were able to measure galaxies that were 20 times as distant as before. And this is the plot of their new data. All the old data is contained in the little small box in the corner. This time, it was much more obvious that the points lay on a straight line. So Hubble's law states that the recessional velocity of galaxies is proportional to their distance from us. And here it is in mathematical form, which simply states that the velocity v is proportional to the distance, and the constant of proportionality h0 is called the Hubble constant. Although it is called a constant, the value of h0 has changed through the years, both because observations have improved and because it must be calibrated as the universe expands. So the first implication of an expanding universe is that if it is expanding, then it was smaller yesterday than it is today. And smaller the day before yesterday than it was yesterday. So if we continue back in time, it implies that the universe has a beginning. So if the universe has a temporal beginning, and if we can calculate how long it has been expanding, we can then calculate the age of the universe. In other words, when we talk about the age of the universe, what we mean is the length of time it has been expanding. So the expansion time t is simply equal to 1 divided by the Hubble constant h0. Now, with the value of h0 that Hubble had measured, the age of the universe came out to approximately 2 billion years old. That, however, posed a problem, because geological evidence at the time put the age of the Earth around 3.6 billion years old. So obviously the universe could not be younger than the Earth. Today, the best calibrated values of H0 give the universe an age of 13.8 billion years. However, very recently there has been some disagreement on the current value of H0, so this value may change in the near future. Let's take a look at the state of cosmology in the 1930s. Einstein and Hubble were not much interested in cosmological implications. Einstein's focus was to find a single law of physics to unify the fundamental forces, and Hubble was really only interested in recording accurate astronomical observations without any interest in their cosmological significance. Einstein's only connection with the subject came in 1931 when he personally saw Hubble's data. The data was so convincing that he finally accepted that the universe is not static, but is expanding. Now recall that Einstein had so firmly believed in a static universe that he introduced a cosmological constant to his equations to balance out a gravitationally contracting universe. But with an expanding universe, there is no need for a cosmological constant, so he dumps it, calling it the greatest blunder of his career. We'll see in a future lecture that maybe it wasn't a blunder after all. Einstein then apologized to Lemaitre, admitting that his theoretical model of an expanding universe was correct. The main figure during this period is Father George Lemaitre. Recall that Lemaitre had found solutions to Einstein's equations that supported an expanding universe. His findings were reported in his 1927 paper, but no one paid much attention to it until 1930. In his paper, he introduces the idea of a dynamic universe. And he also predicts that galaxies should be racing away at speeds that were proportional to their distances. After Hubble's discovery, Lemaitre's paper resurfaced. Gradually, word spread throughout the scientific community, and there was a growing admiration for the perfect match between Lemaitre's theoretical predictions and Hubble's observations. Lemaitre's theory of an expanding universe came to be the accepted theory after Einstein publicly endorsed Lemaitre's model in 1931. An expanding universe implies that it was smaller and smaller as we go back in time. Lemaitre reasoned that at some finite time in the past, all the matter and energy of the universe was concentrated into what he called a primeval atom. Now, although Lemaitre's cold primeval atom is not the hot Big Bang that has come to be known, it was the first suggestion of an initial moment for the beginning of our universe. Lemaitre's insightful work would become the framework for the Big Bang theory, and he is rightly called the father of the Big Bang. With the advent of World War II, the focus shifted to nuclear physics. World and personal events would combine to stop Lemaitre from further developing his cosmic theory. The cosmic theory baton was now passed to Russian immigrant George Gamow in the early 1940s. Gamow's interest in the models of the early universe was in relation to the formation of elements. He was the first to bring the role of nuclear physics into the evolution of the universe. Gamow reasoned that if the universe gets smaller and smaller as we go back in time, it becomes increasingly more dense. And as matter is compressed, it generates heat. So the early dense universe would have been very hot. He assumed that the extreme heat of the very early universe would have broken down all the matter into its most fundamental particles. So the very early universe would be a hot, dense soup of fundamental particles that would eventually combine to form atomic nuclei as the universe expanded and cooled. So Lemaitre's cold primeval atom explosion becomes the hot Big Bang expansion we know today. Now, the task of calculating all the nuclear reactions occurring in the constantly evolving early universe was very daunting. As the universe expands, it would become cooler, the density would decrease, and the mix of particles would be constantly changing depending on the nuclear reactions that would have already taken place. Gamow simply did not have the mathematical skills to make these calculations. Eventually, in 1945, Gamow received his much-needed mathematical help when he took on Ralph Alpher as his graduate student. Gamow and Alpher spent the next 3 years working through their calculations, applying concrete physics to mathematically model the conditions and events of the early universe. Even though Gamow's goal was to explain how all the elements may have formed in the early universe, their calculations were telling them that the universe would have cooled down too much during the first few minutes to allow for the heavy elements to form. But they did predict the amount of hydrogen and helium nuclei that would form within the first 300 seconds of the universe's existence. And amazingly, that amount has been observationally proven today. In 1948, they published their findings in a paper which has come to be known as the Alpha Beta Gamma paper. Now, Hans Bethe was not an actual contributor, but Gamow thought it would be fun to add his name just as a pun on the first 3 letters of the Greek alphabet. This paper has become a milestone in Big Bang theory. Shortly after this, Alpher started a collaboration with another colleague, Robert Herman, and they realized that as the universe expands, it would steadily cool down. They calculated that the initial radiation would have cooled down to about 5 Kelvin, close to absolute zero, and predicted that it should be observable. This radiation should be observable as a faint microwave light coming from all directions of the universe. Unfortunately, it would take another 15 years before this light was detected. Now, Gamow, Alpher, and Herman would continue to work and collaborate through the early 1950s. But even though the Alpha Beta Gamma paper would eventually be considered a milestone paper in Big Bang history, and even though the process of the formation of hydrogen and helium nuclei within the first few minutes of the early universe would become known as Big Bang nucleosynthesis, and even though the predicted leftover radiation of the early universe would be discovered as the cosmic microwave background and provide the observational proof of the Big Bang model, they were not taken seriously at their time, and their work remained relatively unknown. During the late 40s and throughout the 50s and into the early 60s, there was still much disagreement between the ideas of an expanding universe with a temporal beginning versus the idea of an expanding yet eternal universe. In 1949, the British physicist Fred Hoyle proposed an alternative theory. It was called the steady-state model. In this model, the universe is expanding, but matter is being continuously created to form new stars and galaxies so that it maintains a constant density. We will see that this model will be proven incorrect, but for a while, cosmologists were split between these two camps. Hoyle was the most aggressive critic of the temporal beginning model, but in a funny twist of history, he accidentally gave it its name. While speaking for a BBC radio broadcast, and in an effort to deride or ridicule the opposing theory, he said that he could not see any good reason to consider that the universe would have started with a Big Bang, and the name stuck. Besides accidentally naming the Big Bang theory, Hoyle's real contribution to the study of the universe was in solving one of the weaknesses in the Big Bang model. According to Gamow and Alpher, the Big Bang could not account for the formation of elements heavier than helium. In 1957, Hoyle, together with 3 other collaborators, published a paper describing how nuclei of elements could be formed in the evolution of stars. We will talk much more about this in lectures 4 and 5. There were now two dominant and competing theories of the universe. One was the Big Bang model, in which the universe had a temporal beginning when all matter, energy, space, and time were in an initial extremely hot and dense state, and then it expanded and cooled, allowing matter to form and condense into stars and galaxies. The other was the steady state model, in which the universe had no temporal beginning, and as it expanded, matter was continuously created. These were two very different theories, but they had one thing in common. There was no conclusive observational evidence in support of either one of these theories. Because of the lack of observational evidence, cosmologists were divided at the time. Two Princeton physicists who supported the Big Bang model were Robert Dicke and James Peeble. James Peeble just received the 2019 Nobel Prize for his contributions to cosmology. They reasoned that the Big Bang must have released a tremendous amount of radiation, and a remnant of that radiation should still be detectable today. As they worked out the details of the background radiation, they predicted that due to cosmic expansion, the radiation should be in the microwave range and cooled to a temperature of about 3 to 5 degrees above absolute zero. Now recall that Gamow, Alpher, and Herman had already predicted this in 1948, but their work was not known by Dicke and Peebles. As Dicke and his team were getting ready to build an antenna to detect the cosmic radiation, they were scooped, in Dicke's words, by a pair of scientists from Bell Laboratories, Arno Penzias and Robert Wilson, who in 1965 accidentally made one of the most important discoveries in cosmology, the cosmic microwave background. Now, Penzias and Wilson's goal was to study various radio sources throughout the sky using Bell Laboratories' 20-foot horn antenna. As they were testing the antenna, they identified a persistent and constant noise, regardless of when and where the antenna was pointed. This noise or signal was coming from all points of the sky. Their first thought was that there was some noise or interference from the antenna itself. So they checked every element in their antenna, wiring, faulty electronics, misalignments, everything they could think of. At one point, they even thought it could be caused by the white dielectric material, or pigeon poop, found in the antenna. But they could not identify the source of the constant noise. Shortly after, Penzias was made aware of a draft paper by Dicke and his team in which they explained that the Big Bang model should produce an all-pervasive cosmic radiation. Penzias finally understood the source of the noise that had plagued him for a year. He immediately called Dicke to tell him he had detected the cosmic radiation. At the time of the phone call, Dicke was in a meeting with his team to plan the building of the antenna to detect the radiation. And after his conversation with Penzias, Dicke turned to his team and famously said, "Boys, we've been scooped." The discovery of the cosmic microwave background was the observational evidence needed to support the Big Bang theory. So the steady-state model was abandoned, and the Big Bang theory was finally on firm footing and became the dominant theory in cosmology. Penzias and Wilson received the Nobel Prize in 1978, even though at the time of detection, they actually had no idea of what they had discovered. This is an all-sky map of the cosmic microwave background. We will talk much more about this in upcoming lectures, but for now, this is basically a snapshot of the universe when it was only 380,000 years old. The next exciting discovery in the history of the universe was that there's some other kind of matter out there which we call dark matter. Although it has not been directly detected yet, its gravitational effects have been observed. To be fair, the Swiss-American astronomer Fritz Zwicky was the first to put forth the idea of dark matter in the 1930s. He studied the motion of galaxies within the Coma cluster, and what he found was that galaxies were moving too fast for the amount of visible matter, or what we now call ordinary matter, that was in the cluster. So he concluded that there must be matter that we don't see that would produce a gravitational field to support the measured speeds of the galaxies. He called that unseen matter dark matter. Unfortunately, no one took him seriously at the time. In the 1970s, the American astronomer Vera Rubin made a more convincing set of observations. With improved sensitivity and resolution of radio telescopes, she set out to measure the orbital speed of gas and dust at the edge of the Andromeda Galaxy. And what she found was that the orbital speed did not decrease as expected by the gravitational laws of physics. She concluded that there must be some unseen stuff out there that is producing a gravitational field. Many observations since then have confirmed her results. Today, 3 independent types of observations have confirmed the effects of dark matter. We will talk about all these 3 methods in our last lecture, but for now what is important is that all 3 methods give us the same result. The amount of dark matter must be 5 times the amount of ordinary matter in the universe. Now, throughout the 20th century, telescopes were getting better and better, but it was starting to become clear that to continue studying the far reaches of the universe, telescopes had to be away from the effects of the Earth's atmosphere. The Hubble Space Telescope was launched on April 24, 1990, aboard the Space Shuttle Discovery on an original 15-year mission. It has been serviced 5 times during Space Shuttle mission and was supposed to have been brought back to Earth at the end of its mission. But with the end of the Space Shuttle program, that is no longer possible. This year, the Hubble Space Telescope celebrates its 30th anniversary in space. And as long as it continues to function, it will stay in orbit. Eventually, it will be simply guided to deorbit into the ocean, maybe in the mid-2030s. The Hubble Space Telescope is the most complex multi-instrument spacecraft ever built, and it has certainly been one of the world's greatest explorers. Not only has its spectacular images shown us a view of the universe beyond our imagination, but it has helped us rewrite our knowledge of the universe. We will see many of Hubble's beautiful images throughout the rest of this course, and more importantly, we will see what we have learned about the universe through these iconic images. Although Hubble is the most famous space telescope, there are others. Hubble is optimized for the visible light range. The other telescopes are designed to detect different parts of the electromagnetic spectrum so as to get a more complete picture of the universe. Here are 3 other space telescopes. The Chandra X-ray Observatory was launched in 1999 and is designed to detect X-ray emissions from very hot regions of the universe, such as exploded stars, clusters of galaxies, and matter around black holes. The Spitzer Space Telescope was launched in 2003 and concluded its mission in early 2020. It was designed to detect infrared radiation, providing a view into regions of space that are hidden from optical telescopes. The Fermi Gamma Ray Space Telescope was launched in 2008 and is designed to detect the most energetic form of radiation, gamma rays, from some of the most exotic and beautiful phenomena such as supermassive black holes, merging neutron stars, and streams of hot gas moving close to the speed of light. The James Webb Space Telescope is Hubble's successor. It is scheduled to launch in March of 2021 and is designed to detect infrared radiation. It will look deeper into space than Hubble and therefore farther back in time. One of the most recent and unexpected discoveries in cosmology is that the expansion of the universe is accelerating. This very unexpected discovery came about after scientists started to wonder about the future of the universe. The Big Bang Theory tells us about the past. The universe had a temporal beginning when all matter, energy, space, and time were all concentrated into an extremely hot and dense state, and that it started to expand from that moment. Since the universe has a past, then it is natural to wonder about its future. So, will the universe continue to expand, or will it recollapse on itself at some point in the future? The answer seems to depend on how much stuff is in the universe. Since every bit of matter exerts a gravitational pull on every other bit of matter, this should create a drag that slows down the expansion. So the idea was to measure the rate at which the expansion was slowing down to determine if the universe would continue to expand slower and slower to infinity, or if it would eventually slow down to a halt and then recollapse. In 1997, two independent and highly competitive teams set out to measure the slow-down rate of the expansion. But what they found was that the current expansion is not slowing down, but it is accelerating. This was a completely unexpected result, but the observations were unquestionably revealing something new about the universe. For the first 9 billion years, the expansion slowed down as predicted, but in the last 4.5 billion years, it has been accelerating. Dark energy is what we call whatever it is that is propelling the accelerated expansion of the universe. But we don't know what it really is. We will talk much more about this in the last lecture. What we do know is that it is a property of space itself, and it makes up about 70% of the energy density of the universe. The other 30% is made of matter, both ordinary and dark. Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the 2011 Nobel Prize for their discovery. So to answer the question about the future of the universe, the real answer is, we don't know. And that's what makes it so exciting. And so we come to our most recent significant discovery, gravitational waves. Gravitational waves are ripples in the very fabric of space-time itself. As gravitational waves propagate, they stretch and squeeze space itself and everything they pass through. They were predicted by Einstein's general theory of relativity in 1915, but Einstein himself never thought they could actually be detected. It took 100 years, but finally in 2015, the first direct observation of gravitational waves was made. The detected gravitational waves were from a massive gravitational event when two black holes merged together to form one larger black hole. We will talk more about this in Lecture 5. Rainer Weiss from MIT and Kip Thorne and Barry Barish from Caltech were awarded the Nobel Prize for this discovery. It should be noted, however, that the Nobel Prize can be awarded to a maximum of 3 people, but the detection of the first gravitational waves was a large international team effort. Besides proving Einstein right once again, the real excitement over gravitational waves is that their detection has given us a new tool to study the universe and has ushered in a new era in astronomy and physics called multi-messenger astronomy. This is the ability to see and study the same cosmic event using multiple types of signals. This gives us a fuller picture of some of the most mysterious phenomena in the universe. The event that truly ushered in this new era was the merger of 2 neutron stars, first discovered in August of 2017. This marks the first time in our history that a cosmic event has been observed in both light and gravitational waves. Already these observations have provided some answers to decades-long mysteries, such as where half of all the elements heavier than iron are produced, and they have confirmed Einstein's prediction that gravitational waves travel at the speed of light. This is indeed a very exciting new era in the study of the universe. So let's summarize our more than 2,500 years of discovery. Often, scientific understanding develops gradually through a series of minor changes. But every so often, our understanding needs a major shift in thinking. So let's take a look at some of these major paradigm shifts. The ancients believed in an absolute universe, with the Earth lying at rest in the center of the sphere of fixed stars. Little by little, the Earth was displaced among the other planets, and the Sun became the dominant and central object of the universe. Then the Sun itself was moved away from the center to the edge of the galaxy, which was considered the entire universe. Then it was discovered that our galaxy is just one among many others. Not only are there many galaxies out there, but they are all moving away from each other, and the farther they are, the faster they are moving. In other words, the universe is expanding. This was the most fundamental shift in our view of the universe. We went from a static universe in which objects are observed to move within the universe, but the universe itself was not changing, to a dynamic universe which actually changes in time. So if the universe is expanding, it has a temporal beginning. Then we discovered that what we now call ordinary matter is not the only matter in the universe. Although not yet detected, observations indicate that there is some other mysterious form of matter, or dark matter, that exerts a gravitational effect on ordinary matter. One of the most surprising shifts in our view of the universe is that the expansion is currently accelerating. We call dark energy whatever it is that is causing this acceleration. And finally, we can actually wonder about the future of the universe. Less than 100 years ago, this was not even a question that we could ask ourselves. It just would not have made any sense. But today we can. And although we don't have the answer yet, at least we can ask the question. So let's go back to our first slide to see if what we know about our universe today makes a little bit more sense. We know that our observable universe is 13.8 billion years old. In other words, the universe has been expanding for 13.8 billion years. We know that the universe started to expand at a moment which we call the Big Bang. We do not know what happened at the actual moment of the Big Bang, and we certainly do not know what happened before it, but we have a pretty good idea of what happens just fractions of a second after. At the beginning of time, all of space, time, matter, and energy were contained in a region of infinite density and zero volume. And for reasons that are really not known, the universe expanded from this initial extremely hot and dense state and evolved into the very cold and sparsely populated universe of stars and galaxies we see today. The expansion rate of the universe slowed down for the first 9 billion years, as we would expect due to gravity. But surprisingly, during the last 4.5 billion years, the expansion has been accelerating. We call whatever it is that is causing this acceleration dark energy. Our best observations today indicate that the universe is made up of 5% ordinary matter, all the planets, stars, and galaxies, about 25% dark matter. Although unseen and yet to be discovered, there is abundant gravitational evidence that it exists, and about 70% dark energy, that which propels the accelerated expansion of the universe. So hopefully now you have a better understanding and appreciation for the historical and scientific progress it took to achieve today's knowledge. So where do we go from here? Well, many answers to today's questions lie in the early universe. The more we know about the formation of the universe, the more we can know about its future. The Hubble Space Telescope has captured images of some of the first galaxies, but anything before that has been redshifted too much by cosmic expansion, and it is not within Hubble's range. It is hoped that the James Webb Space Telescope will be able to capture the radiation from the first stars, formed about 200 million years after the Big Bang. We have already detected the oldest light in the universe, or the cosmic microwave background, and ongoing analysis of this radiation will continue to give us insight into the very young universe. But this is as far back as we can ever be able to see. For reasons that will be better understood in Lecture 3, light is trapped in the very early universe. It is only able to come out once the universe has cooled down enough, allowing light to freely travel through the universe. So how do we know about what happens before that moment? What we know so far comes indirectly through particle physics. We'll talk more about that in Lecture 3. But with the recent detection of gravitational waves, it is hoped that we can now get direct information from this period. So our final question for today is, will future discoveries bring about new paradigm shifts in our understanding of the universe? Only time will tell. In the next lecture in this series, we will travel nearly 14 billion years back in time and see how the universe emerges from its initial extremely hot and dense state, a moment which we call the Big Bang, and evolves through expansion and the action of gravity to form the first stars, galaxies, clusters of galaxies, and growing into what is known today as the cosmic web. I hope you've enjoyed today's brief historical survey, and thank you for watching.